Welcome to Leonard Springs Nature Day. We hope you're ready to watch and learn as we explore our local environments. Remember, you must follow along in your student journals and use the materials provided in your Nature Day activity kits to complete today's lesson. Let us start by defining the ecosystem we are studying. Creek ecosystems are flowing waters that drain the landscape and include the living, biotic interactions amongst plants, animals, and microorganisms, as well as non-living or abiotic, physical, and chemical interactions of its many parts. Creek ecosystems are part of larger watershed networks where smaller streams drain into mid-sized creeks, which progressively drain into larger river systems. For the remainder of today's lesson, we are going to focus on freshwater creeks that run through Indiana. Before we continue the lesson, you will need to gather the creek station materials provided in your Nature Day activity kit, as well as your own water sample to study. Your water source can be directly from the tap or from a store-bought bottle. To assess the water quality, we are going to evaluate the physical, chemical, and biological properties of our sample. To learn more, let's visit one of our naturalists in a local creek habitat.
Hello everybody and welcome to Creek Station. So I'm Dominic Hepner. I'm one of the City of Bloomington Parks and Recreation Natural Resource Education Specialists, and I'm going to be kind of guiding you through Creek Station.
To begin, let's turn to pages 4 and 5 of your Nature Day journal. When evaluating water quality, researchers measure two physical properties: turbidity and temperature. Turbidity is the measurement of how clear the water is. High turbidity means that there are a lot of particles suspended in the water and light cannot get through. Low turbidity means that there are fewer particles in the water and it is more clear. For today's lesson, we're going to assume everyone has access to a clear water sample with low turbidity. Temperature measurements can tell us how hot or cold something is. It can also indicate how much oxygen is available in the water. To help explain this, let's take a quick look at the dissolved oxygen and temperature comparison graph on your Creek Station handout. To support aquatic populations, healthy streams require optimal levels of oxygen. To get water temperature measurements, researchers use several types of sensory devices. For today's lesson, we'll just use a little household thermometer.
Now my thermometer lists both Fahrenheit and Celsius. If you have a thermometer, we're going to be using Fahrenheit today. If you do not have access to a thermometer, use an internet or a smartphone or maybe a tablet, anything that you have access to that can get you air temperature. So for air temperature, this has just been sitting out with me. Try not to leave it on any rocks or sitting on the ground. I usually try to hold it, maybe even hang it on a tree, long enough for us to get our air temperature. So I like to leave it for about 10 minutes. So currently our temperature is about 47 degrees Fahrenheit. Now, for our water temperature, you're going to take your thermometer, if you have one, and you're going to place it in your water sample. You want to leave it there, maybe for about 5-10 minutes, just so it has time to acclimate and give you an accurate reading. So I just took ours out of the water, and it's reading at about 40 degrees. So we're looking at about 7 degrees-ish lower than our air temperature. And that's what we'd expect. We generally expect the water to be lower than the air temperature. If the water were to be above that, then I would assume we have some sort of chemical pollutant that's raising our water temperature. Now please record the water temperature in your nature journals on page 4 where it says water temperature under chemical and physical testing.
Now let's move on to assessing the chemical properties of our water sample. Chemical characteristics involve parameters such as pH and dissolved oxygen. For this section, you're going to need a few materials that were provided to you in your Nature Day activity kit.
So you should have a sheet that looks similar to this. This is your temperature and dissolved oxygen sheet. You should have another sheet that's a pH scale. It says pH scale. It has a bunch of pictures. May not be the same color as mine, but they should look very similar.
You should have also received a small pH strip to test your own water sample. Please set the strip in a dry location until we are ready to use it.
Alright, if you can follow along with me on your pH scale sheet, we're going to learn a little bit about pH before we get started. So as you can see, our scale goes from 0 to 14, with 0 being the most acidic, 14 being the most basic, and 7 to 8 being neutral. Now, underneath the scale, it gives you these bars below, and this shows you the range that different organisms can live in. So bacterium has our widest range. We actually call bacterium that can survive on the farthest side, way here into acidic. We call those extremophiles. Then we have a plants and algae range, a carp, looks like insects, catfish, and suckers. So these are fish and insects. We have larger fish. These are bass, bluegill, and crappies, snails, so on and so forth. It goes down. These are optimal ranges. Now, to kind of explain a little bit more about acidic and basic, acidic are going to be things that, they might help break down nutrients, or it's going to be something that's going to break down anything that comes into contact with it. So, lemon juice is a 2 on the acidity scale. It works a little slower, but you think about it, if lemon juice gets in a cut that stings, that's kind of an example of that acidity. Way over here on the basic side, we have things like limestone, ammonia, bleach, lye. These are ammonia and bleach are cleaning products, but these are basic. So if you notice, even though they're basic and they're not like that acidic, if it goes too far this way, it could still be harmful for organisms as well. They need a healthy balance. They need to be right there in that neutral range, which is where we're going to find our own blood, distilled water, and seawater. So this chart's going to come in handy once we get our results. So you can put this to the side for now, but if you ever get confused on what we're talking about with pH and acidic and basic and all that, make sure you reference this chart. So our first chemical assessment we're going to do is pH. So for this activity, you need your pH strip. It should look like this. You'll need your pH scale with example, acid and basics. Yours should look similar to mine, but a little different. And then you'll also need a water source, or sample. For this sample, preferably you'd go outside, get an outside water source, but maybe you don't have access to that. That's fine. You can use any water source you have available. So you can use sink, you can use bottled water. Any water is going to give you some sort of reading similar to what ours is. But primarily you'll need this pH strip, a water sample, your journal, and our pH scale with example acids and bases. Right, now, to use this strip, you're going to take your water sample. I'm just going to use the stream itself, and you'll stick it in there. You don't really have to move it or wash it around any. And wait a few moments, usually about 5 seconds. Then you'll pull it out, and you're going to wait 30 seconds. And then based on the color that the very tip turns, you're going to look at your color chart, and it's going to give you our pH value. Now that we have our pH color on our strip, we have our value. You need to log this in your journal on page 4 in the little box to the right of pH under chemical and physical testing. Now a couple of things to note with this stream. Our pH is going to trend a little higher than normal. So typically we would expect a pH around 7, but in Indiana we see pHs closer to 8, 8.5, and that is because we have so much limestone. And if you look at your chart, limestone is actually here. It's above baking soda. It's between an 8 and a 9. So that limestone, as it erodes, it raises the pH, so it trends towards being more basic. For the final chemical test, we're going to move on to dissolved oxygen and dissolved oxygen saturation. So as we talked about, as temperature increases, oxygen levels in the water decrease, and then we might see a decrease of specific macroinvertebrates and other vertebrates and non-vertebrates that we are using to determine stream health. So we can actually test for this. We can actually find out how many parts per million of oxygen there is in this water. Then we use that number to figure out our saturation. So what is this water's potential to hold more oxygen or less oxygen? So to do this testing, I use what's called an ampoule. So this ampoule comes preloaded with all the chemicals I need to test the water. So we'll grab our sample here. Now you can't do this at home, but you'll see the results of what I do, and we can kind of use this with your numbers to at least see what we're doing. So we fill it up to exactly 25, so I'm a little over now. Stick our ampoule in, break it, and then all the water shoots in there, and it's already starting to turn blue. So blue is our activation color. So then I'm going to tip it a few times, and we'll let it sit. Comparing our ampoule to our standards gives me our current DO levels. So right now we're sitting at about a 9, right? And you'll place this in your journal where it says dissolved oxygen. Now I need you to take out your temperature, dissolved oxygen, and macroinvertebrate sheet. We're going to be using both sides of it this time.
The front of the sheet explains how dissolved oxygen is essential for the health and survival of organisms in aquatic environments. Macroinvertebrates, like the ones we are going to study today, depend on oxygen in the water to breathe, as they cannot produce their own like plants do. A graph is shown here to emphasize the relationship between water temperature and oxygen levels. Again, it is important to remember as water temperatures rise, oxygen levels decrease. On the back of the sheet, there is a conversion formula and a graph that you will need to use to help calculate the dissolved oxygen percent saturation of our water sample. This measurement tells us the percentage of dissolved oxygen concentration relative to the temperature of the measurement depth. To calculate this value, we must first convert our water temperature from degrees Fahrenheit to degrees Celsius. The F to C conversion, Fahrenheit minus 32 times 5 divided by 9. To do this conversion, plug in your water temperature measurement into the formula provided using a calculator or smart device. Using a straight edge, a ruler or a piece of paper will work. Draw a line from the temperature value, Celsius, to the dissolved oxygen value. The point at which the line crosses the middle line, or the saturation scale, is the percent saturation of oxygen. Please record this percentage on page 4 of your student journal. Our final water assessment involves measuring biological signs. Biological indicators of water quality include algae and aquatic organisms like macroinvertebrates. To measure these populations, researchers conduct field inventories using dip nets and other apparatuses. But before we can do that, there are a couple terms we need to discuss.
Invertebrates versus vertebrates. So an invertebrate is an organism that does not have that spinal cord. Think of it as it's probably going to have an exoskeleton, or it's going to have some other skeletal muscular structure, but not that spinal cord that we see in most mammals and other vertebrates like fish and reptiles and things of that nature. So these organisms are invertebrates, so they're organisms that do not have that. Another term that we need to know is intolerant versus tolerant. If something is intolerant, that means it cannot survive. It cannot be in that kind of environment. It cannot be around that stimulant. This is intolerance. If something is tolerant, it means that it can. So in our example of heat or pollution, if something was tolerant, that means with a lot of pollution, or if it had a lot of direct sunlight, it would still survive. If it was intolerant, it would not. So when looking for macroinvertebrates, there's a couple of different methods we can use, and it really depends on what our purpose is. So if we were out here doing a formal survey to get a WQI score, so a water quality index, then we would likely use this net, which is called a kicksane. These are actually really easy to make, so this is a homemade one. We use 2 pieces of PVC pipe and a little mesh, and then we weight the mesh at the bottom. So that way we're going to try to get as close as a seal as we can get to the bottom there, so nothing goes underneath. Now this net does take 2 people, so you can't really use it when you're alone. But the good side of this is when using a kicksane net, we only have to use it 3 times. So we have to get 3 sample sets using this, as opposed to our other net, which you'll see in a little while, which we would have to use 30 times to sample a similar area. So if we could stick it in, we'll demonstrate it here. So the cool thing about this net is one person gets to have all the fun, and you stand upstream and you dance. So you just kick around all the rocks. You really want to get it kind of sloshed up as much as you can. And then the downstream person will hold the net in place. And after a little while, we scoop it up and we see if we caught anything. Scoop it up, we place it on something flat, we look around in it. And what we're looking for is anything that's alive. We actually did catch some things. So it looks like we have some sow bugs, these little dots here, and some leaves, and that's really about all we got. This here is a dip net, and we use it when we're doing less formal surveys. So maybe I'm coming out here trying to decide if I need to do a full evaluation, or I'm just out here on a tour or something. We use a dip net. The reason we use it in a less formal setting is it takes 30 dips of this net to equal 3 dips of the kick-seine net. And the way this works, it's pretty simple. You stick it down in here, and we're trying to mess with the substrate. So the substrate is that layer of sediment that's right on the bottom that this water's flowing over. So we'll disturb it just a little bit, kind of hop it up and down, and then after a while, we take it out and we do the same thing. We look through it, see if we got anything. This one, it looks like I just got a bunch of seeds and maybe some leaves. But we do that 30 times, and it would give us a good indicator on our stream health based on our macroinvertebrates. Alright, so for this next portion of Creek Station, we're going to be catching macroinvertebrates using those nets and determining the health of our stream based on what's living in it. So I already went through and caught some for us, which we'll get to look at here, but each of you needs to grab your sheet like this. This is your macroinvertebrate identification key. And there's a few things that we need to note on it. So there's these groups here. It says 1, 2, 3, and 4. And that lets you know how tolerant or intolerant they are of pollution, right? And it's on a scale. So group 1 is very intolerant. So if we see group 1 macroinvertebrates in our stream here, then we know that it's relatively healthy. It's not too polluted, they're able to survive. And then it goes down accordingly. All right, everyone, so if you are looking at your journal and still following along, we are on the macroinvertebrate section of our Creek Station pages. And this is our first organism. So you're gonna need that journal, and you're also gonna need your macroinvertebrate identification key. So right now, what we're looking at are these little, they look almost like dried bird poop on the bottom. They're little collections of sticks and soil and sediment and just little particulate that the caddisfly uses when it's a larva to stay safe. So those are caddisfly larvae. So if you look on your macroinvertebrate identification key, you should be able to find the caddisfly. Now, in your journal, under macroinvertebrates, you should write the name of the organism, which I've given you this time, the caddisfly, under 1. And then where it says tolerance to pollution, you would look where our group levels are. So this one happens to say group 1, very intolerant of pollution. That's what you'd write there. You can also, if you'd like, under name of organism, once you have the name, you could draw a picture so you can remember what it looked like, or anything else you might need to help you identify this organism. Also, in the name of organism box, you could include some defining characteristics. So for instance, with this caddisfly larva, we see that little sheath, that little, almost like a cocoon that it builds, and you could call it a shell if you wanted, but that's a good defining characteristic of what a caddisfly looks like. Okay, so this next species that I'm going to bring up, this is your first self-identification. So you're going to take your Nature Day journal, you're going to look at your tolerance guide, and you're going to find this organism. You're going to write its name, maybe some defining facts, draw a picture, and then you're going to put its tolerance level.
Now pause the video and record this information in your student journal.
Alright, now we're moving on to our third species. This is going to be the second organism that you identify on your own. So you're going to use the number 3 box under macroinvertebrates. This organism, a few things to note, is it's very, very flat, and it has a hammer-shaped head. Also, what you might not be able to see in the photo is this species actually has 2 eyes that are angled and sort of on the top of their head. For our fourth species on your macroinvertebrate page of your journal, it's going to be this little guy. A few things that you might not be able to see very well. Notice that he does have 3 tails. That's going to be really big in helping you identify what this is using your macroinvertebrate key once again. One other thing to note about this organism is that these little things you see at the very bottom, they look like tiny, tiny legs right at the base of those three tails. Those are actually gills. That's how this organism breathes. So it's another cool fact you could put. Once you've identified it, make sure you write it on the list, draw me a picture, maybe put some cool facts, maybe those three tails, and also write its tolerance level in the sheet. Alright, to wrap it all up, you should have 4 organisms or species listed on your macroinvertebrate page of your journal, and you should have their name, maybe a picture, a fun fact, but more importantly, their tolerance level. So using those tolerance levels, if they're intolerant, maybe they're tolerant, we can move on to our final question in our journal, which asks you, is our stream healthy or not based on the tolerance level of those organisms and the organisms that we found? So looking at all the ones on your sheet and their tolerance level, let's make that prediction and write in there what you think. Do we have a healthy stream? Did we find enough different organisms to classify it as such? Or maybe our stream isn't healthy and it needs some help. We need to get out here and figure out what's going on with it. So write your prediction and anything else that might help you make that prediction in that last space on your journal page there.
At this point in the lesson, you should have completed both pages 4 and 5 in your student journal. Thanks for watching. We'll see you next time.